the share. So for the people who are already here, I'd like to welcome you all to our second webinar series. We organized one last year, and I'm really happy to be able to present you a second series this year on dye tracing in practice. Just some practical information for the participants. It would be good to shut down your microphone and your webcam, just not to disturb the presenters during the presentation. So the webinar will be recorded, and of course, with permission, it will be distributed afterwards. And after each presentation, you can there's a small period of time for questions and answers. So you can either raise your hand at the top of your screen, or ask your question directly in the chat box. So for today, I'm really happy to present you four presenters for 3 presentations. So we will start off today with Romain. He's a PhD student at the University of Namur at the Department of Geology. And he will talk to us about the multi-peaked breakthrough curve in karstic rivers. Next, we have Elke Mugova and Christian Wolkersdorfer. Elke is a mine water researcher at TU Bergakademie Freiberg. She's also a conference organizer. I hope she will talk to us a little bit more about the conference as well. And she's a guest researcher at South African Research Chair of Acid Mine Drainage Treatment. Christian Wolkersdorfer is a professor. He's also elected member of MASSAf and the president of the International Mine Water Association. And they will talk to us about fluorescent tracers in mining influenced water. And our last presentation today will be by Pierre Jamin. He's a hydrogeologist and also the founder of the startup company Nagaré. And he will talk to us a bit more about risk analysis and management of polluted aquifers using a methodology that was developed by himself. So let's start with the first presentation. Romain, if you please, you can.
Yes, I share my screen.
Yes.
Is it working? Okay, perfect. So good afternoon, everyone. I'm happy to be here to talk to you about a project we did in my PhD thesis, which is still ongoing. The title of my presentation will be Multi-Peaked Breakthrough Curves in Karstic Rivers, and we will talk especially about the effects of a diffluence-confluence system. So, as you may know, a diffluence-confluence system, so as illustrated on the figure here, is when a river splits into 2 or more conduits and merges back at the confluence. And if you measure the tracer breakthrough curve downstream the system, you can sometimes observe a double-peaked breakthrough curve if the conditions are right. And there are not so many papers about double peak induced by this kind of system. There are some papers that talk about this with laboratory designs, but not so many with field studies. So the objective here is to study the effects of such a system on a tracer breakthrough curve, just like the figure here, but on the field in an actual cave. So we started with on-site tracer tests, which were done in An-sur-Lesse in Belgium. As you can see on the map here, An-sur-Lesse is just in the south part of Belgium, and especially if you zoom in on the region, you can see that the river Lesse infiltrates inside the Massif de Boine, which is composed of limestone, of course, and then reach back the surface a few kilometers later. If we zoom on the cave, and especially the river, we have a map here of the river inside the cave. You can see on the right side of the figure, Gouffre de Bellevaux, which is the point where the river goes inside the cave. And the day we did the tracer test, there was 5.5 cubic meters per second of flow rate. Later, inside the cave, there is a first diffluence where Réseau Sud, a small portion of the water, goes into the Réseau Sud network. There is 0.2 cubic meters per second, but the rest, the majority of the flow, 5.3 cubic meters per second, continues in the main channel. And then there is the part that is interesting for us, is in the square box here. We zoom in there and we have a major diffluence-confluence system where there is 1.4 cubic meters per second going right inside the stick stream and 3.9 cubic meters per second going left inside the derivation stream. So this is very interesting for us because this is exactly what we want to study. So of course, we did some tracer tests, we placed some fluorometer, and you can see that the river merges back together and goes out of the cave with again 5.5 cubic meters per second on the top of the figure here. So we placed some fluorometers, the red points, which were of course fluorometers from Tracois, as you can see on the picture on the left. And there is one fluorometer in at the beginning, at the inlet of the system. This is to see the main signal coming inside the system. And then we have two fluorometers in each streams. So FS1 and FS2 for the stick stream and FD1 and FD2 for the derivation stream. We also have a fluorometer in the small stream Réseau Sud, RS, which is a minor stream. And then we have a final fluorometer at the outlet of the system on the top of the figure out here. This is where it will be interesting because this is supposedly where we would observe a double peak if there is one. We also did some solute transport modeling in this system. So we use the Otis model, which is a 1D solute transport model designed for streams and river, which is based on a transient storage scheme. So as the figure shows, there are, the model consider a small storage zone along the stream, such as a side pool or the river sediments that can hold the tracer for some time. The domain is divided into reaches, which are again divided into individual cells. So each reach has its own parameters. There are two different models, one for the derivation stream and one for the stick stream. So this is two separate models. The parameters used for the model are the flow rate, of course, the concentration. So the flow rate we know because we estimate them using the fluorometer. We have the breakthrough curve. We assume 100% recovery rate for all fluorometer, and we get consistent value for all of them. So we assume it was working nice, and this is perfectly correlated with the gauging station, which is outside the cave. We did not measure the flow rate because the field conditions were not adequate for this. Then we have the concentration, which are calculated by the model as functions of time at various locations along the domain, which give us the simulated breakthrough curve for each fluorometer. And the remaining parameter, so A, AS, D, and alpha, must be calibrated. So A and AS are the channel cross-section area, D is the dispersion, and alpha is the exchange coefficient between the main channel and the storage zone. The calibration of this parameter is done with the data from injections 1 and 2. I will talk to you about this just after. And this is validated by injections 3 and 4, and also by field measurements of stream sections when possible. So we did some measurements on site about the section area of the stream. This was done, for example, in the Styx stream with a sonar boat we use. This is a speleologist from Ghent. They designed a boat with a sonar on it that can measure the depths with a high frequency. And so the speleologist there just controls the boat. He's a skilled pilot. And so we can get this kind of results where you can see the depths in the colored dots here. And you can see this is the location of the fluorometer FS1. I told you just before about this. And for example, in this section, the values we have from the calibration match correctly the actual measure we have of the stream section. So for the results from this field tracer tests, first of all, we did 4 injections, and the first injection, we put 50 grams of uranine, fluorescein, in the derivation stream, so the left stream only. We have, of course, 3 breakthrough curves, one for the first fluometer FD1, one for the second fluometer FD2, and one at the outlet out fluometer. You can see the breakthrough curve. This is the circles here on the figure on the left, on the right, sorry. This is the breakthrough curve from the fluometers. So this is working quite nicely. We have 3 breakthrough curves with different time scale, of course. You can see the first curve is starting after about 2 minutes and ending after about 10 minutes. The second one is only appearing after about 8 minutes. So we have the different values here. And then we want to calibrate the model based on that. So we divide the stream into different reaches. So we have RD1, RD2, RD3, and R out, which are different lengths. And we have the different parameters. So section areas, alpha, and dispersion. And the resulting curve from the model are given in the graphs. You can see the lines. This is the Otis model. So the goal here was to change the parameters so that, of course, the Otis model curve, the simulated curve, match the curve from the actual fluometer. This is quite working well. And here you can see that the specificity here is that the first reach, RD1, has a very small section area. This is due to mainly because it's a very fast flowing section. You can see that the time it takes for the tracer to arrive is very, very small compared to the length of the stream. So yeah, the model suggests that the section area is very small, and this is of course validated by the field observations. Then for injection 2, we did the same on the right side this time, so the stick stream. So we have 3 curves again, FS1, FS2, and out fluometer. All of them give a nice signal with different time scale again. We calibrate this and we get these new parameters here. And we get the curve, the simulated curve here, which match correctly the measured breakthrough curve. So this is the first 2 injections. This is used to calibrate the model. And then we have the third injection where we put 20 grams and 30 grams of uranine in both sides at the same time, just to see what happens. And we get 5 breakthrough curves, one in FD1, in FD2, one in FS1 and one in FS2, and of course, breakthrough curve at the outlet fluometer. For FD1 and FD2, we have very similar signals to injection 1. For FS1 and FS2, we have similar results as for injection 2. And for the out fluometer, as you can see, we have a double peak. This is because the first peak is coming from the derivation stream, which is much faster. And the second peak is from the stick stream, which takes much more time to arrive. The model, the Otis model is the line, and you can see that the line on the left side of the figure, this is the curve from the derivation from the model. And if we combine this curve with the curve coming from the stick stream, so on the right side of the figure, we get the double peak. This is the dashed line on the out fluometer. And this double peak seems to match correctly the double peak measured on the fluorometer. So that means the model can successfully model the combination of the 2 peaks into a double peak breakthrough curve. And then injection 4 is injected at the Gouffre de Bellevaux. So this is the entrance of the cave, well, the entrance of the river inside the cave, which is 1,500 meters upstream. In that case, we get a signal at all fluorometers, so in FS1, FS2, FD1, FD2, and out. But this time we do not have a double peak. So as you can see, this is due, the model suggests that this is due to the fact that the peak coming from the sticks, which is always a bit late compared to the derivation stream, is just masked behind the tail of the first peak coming from the derivation. This is what we see on the top breakthrough curve at the out fluorometer. So if we inject further upstream, we don't have a double peak compared to if we inject closer. We also have a small signal coming from the Réseau Sud, the small stream of 0.2 cubic meters per second. But as it is a small impact, we do not really study this. So the conclusion from those field tracer tests is that the calibration of the Otis model was successful. For a proximal injection, so for injection close to the system, so injection 3, we have a clear double peak that is visible at the outlet of the system, and it is well reproduced by the model. And the double peak is due to the contrasted travel times between the two streams. This is mainly due to the contrasted section area. So as you saw, the derivation stream has a much faster flow because of the smaller cross-section area. And we also have the presence of the two sumps in the stick stream. So I didn't tell you, but on the figure earlier, there was two sumps shown on this stream, which can induce slower flow. And for the distal injection, no double peak occurs. The model suggests the two curves are merged into one single peaked breakthrough curve. So the distance of injection seems to have a strong influence here. So the question we have is, what about the influence of the contrast interval time? Can we quantify this? What about the influence of the distance of injection? And what if the influence of the distance of sampling has also an importance? What if the distance at which we place our fluorometer at the outlet of the system is also important? And finally, what is the influence of the transport parameters, such as dispersion, for example? So for this, we modified a little bit the model. We first changed the injection distance. As you can see here on the first line, A, we change the distance of injection, then we change the distance of sampling. Then as a third attempt, we change the stream length. First the left one, then the right one, for example. And then the last thing we changed was the dispersion. We changed it just to see if it has an impact on the double peak. And the results are interesting because if we change the distance of injection, we get this. So if we inject at 0 meter distance, so basically we inject at the diffluence, we have double peak. But as soon as we go further upstream, we do not have a double peak anymore. The two peaks start to become merged into a single peak. So we have, after about 150 meters, we do not have a double peak anymore. We still have a point of inflection in the tail of the curve until about 800 meters, when we don't have any sign of the occurrence of the double peak. This is the same for the distance of sampling, so the distance at which we place our fluorometer downstream. If we place it at 0 meter, so at the confluence, we get a clear double peak. And if we place it further downstream, the double peak become merged into one single peak until at 800 meters, we do not have any sign that there is a double peak, in fact. If we change the stream length, so for example, here for the first column is for injection 3, so the injection done close to the system. If we shorten the derivation stream, well, the first peak arrive even earlier. So it means that the double peak is even more clear. But if we change the stick stream, well, the second peak this time comes earlier. So that means that the two peaks become simultaneous. So we do not have a double peak anymore, but rather one single peak combining the two curves together because they arrive almost at the same time at the outlet. And for ejection 4, the stream length doesn't change that much. It changes a bit the shape of the curve at the outlet, but it's still one single peak. And finally, if we change the dispersion, as you can see, it doesn't change that much. The difference between the gray curve and the black curve is not clear. There is very slight change, but yeah, it doesn't change that much. So the conclusion from this modified Otis model is that the distance of injection has a very strong influence on the occurrence of a double peak breakthrough curve. And for An-sur-Lesse, specifically for An-sur-Lesse, the double peak is merged into a single peak after about 150 meters. But a point of inflection remains visible until about 760 meters. This is the same for the distance of sampling, so the distance of the fluorometer. It has a strong influence on the observation of a double peak breakthrough curve. And for An-sur-Lesse, it seems that the double peak is merged into a single peak if we place our fluorometer after 600 meters, but a point of reflection can remain visible until 1,000 meters. Of course, the contrast in travel time has a strong influence. This is the key factor. But the dispersion seems to have little to no influence on the double peak. So one of the conclusions is that the merging is all about the spread of breakthrough curve along the time axis. If we inject or measure further from the system, well, we have longitudinal dispersion affecting the curves, which make them spread along the time axis, which can induce the merging. So yeah, the longitudinal dispersion occurring before the system and after the system are very important for the observation of a double peak. So the conclusions of this work is that a double peak breakthrough curve can be observed downstream a diffluence-confluence system if the injection is done close enough. The fluorometer is located not too far. The longitudinal dispersion is the key factor here. But the question is how much is enough and where is too far? How can we know that we inject close enough and how can we know that we place the fluorometer not too far? Well, this entirely depends on the contrast of travel times. So this is dependent on the system. And as we do not know the system characteristic before tracing, well, of course, you all know that dye tracing is a challenge. So the injection and fluorometer location must be chosen carefully. So if your goal is to study diffluence-confluence system inside a cave system, then you have to place your fluorometer as close to the system as possible and inject as close as well. So if you are a good caver, maybe you want to go deeper inside the cave to try to inject closer to the system to see if you have indeed a double peak or not. So yeah, as a conclusion, this has been accepted for publication. So I cannot give you a link yet, but it will be soon published. And here is a video of a 3D model we use. Just it's the first attempt. We are still working on this, but you can see on the left side, the tracer goes very fast. And on the right side, it takes more time, so it arrives later. Therefore, we have a double peak. So that is a 3D simulation of the problem, still a work in progress. We will see what it gives us. And yeah, thank you for your attention.
Thank you very much, Romain. if there are questions, don't hesitate to ask them in the chat or just by raising your hand and asking them. Well, we have congratulations, Romain, from one of the. We have a question from Christian. You can
ask.
You can
Merci bien,
ask.
Romain. You said that you could not measure the flow. What precisely was the reason, and which flow measurement method would you have used?
Yeah, well, in University of Namur, we use a Doppler effect flow rate measurement. This is working for a shallow section, but the problem is that most of the sections are more than 2-3 meters deep. So this was kind of difficult. We tried, but it's difficult with a boat to measure the flow rate. So we tried with the breakthrough curves to see if there is a consistency between each of them, and we have very similar values. So we used that. And we also, of course, checked with the known flow rate of the river less upstream the cave. We have a gauging station which is public, and it gives a very similar flow rate to what we have.
Okay. Yeah, we have similar issues in the mining environment, and what we are using exclusively is the salt tracer dilution method, because for the salt tracer dilution method, the geometry of your channels does not matter at all. So that's probably something you might want to use in the future for measuring the flow. And you can also use your tracer, because you already have a tracer, the sodium fluorescent, for measuring your flow. That's relatively easy. Because it's the same equation, just as an idea for the future.
Yes,
but merci bien. Merci bien. It was really a nice presentation. I liked it very much.
Thank you.
Thank you, Christian. I saw other people raising their hands, but I see that they are gone. So maybe the question was already answered. No, yes, please go ahead. You can turn off your microphone.
Yes, thank you very much, Romain. It was a very good presentation. I don't know if I'm audible. If you can hear me fine.
Yes.
I think Professor Wolkersdorfer has sort of already took a part where I wanted to talk about the salt dilution. But maybe just one question. I see you focused predominantly on using one tracer, which is uranium. Any reason for not using multiple tracers? Why did you zoom in specifically on the uranium? Thank you.
Yeah, the main reason was because at the time the fluorometer we use were one channel for the uranine specifically. We have now with Aqua, of course, we have more than uranine to measure, of course. But at the time we did only have the channel for uranine. That's the main reason. Maybe it would be interesting to see how the transport property of different tracer can affect the way it's done. Maybe.
I hope that answered your question. Yes,
thank you. Okay. Yes, thank you very much. Thank you.
First of all, I have to tell that I'm not a hydrogeologist, so maybe my question might be a bit stupid, but I'll go anyway. Would your model still work if you don't assume 100% recovery of the dye at the end?
We need to know the flow rate to make the model work. So we would have to find a way to know exactly the flow rates of each streams. And one way to do this is to use our recovery rate of our breakthrough curves to estimate the flow rates. So yeah, it would not work. We need to know the flow rate. Yeah.
So if in the system, for example, there would be another small river where some of the tracer disappears, your model wouldn't fit anymore.
Yeah, so if you don't, for example, if you don't have access to the system like we did to place some fluorometer, then you would have to attempt to derive the two curves at the outlet of the system and estimate the recovery rate of each curve to see how the flow rate is separated at the diffluence. So what is the proportion going to the left, going to the right? That would be something that you can do, but it's not easy when you have only the outlet, the curve at the outlet.
Mm-hmm. Okay. There's another question. Go ahead.
Yes.
Yeah.
I think you hear me. Are you hearing me well?
Yeah.
Yes. So I wanted to thank you for this very interesting presentation, because I really like the approach that you combine very hard field experiment with a lot of measuring devices with the numerical approach. And I wanted to ask you, have you already considered to apply it to some system where you have, let's say, a poor knowledge of the geometry behind, and also to larger systems, so where you have kilometers of unknown conduits? Yeah. Because of course there are many other examples of karst systems that are like that, and your application opened probably a new field of investigations. Mm-hmm.
Yeah, I should have put in the last slide a line perspective and should have said, yeah, try this on other systems which are larger scale or different. Maybe it would be very interesting to see if the conclusions are the same or not. The only question is again the access. How can we access the system? Can we place fluorometer inside one of the stream or not? Yeah, that's the tricky question. So it really depends on the caving experience.
Okay,
but because yeah, I should have put this.
Tomorrow there will be also a presentation from one of my institute colleagues, Dr. Franci Gabroszek, about one tracer in a deep alpine karst system in Slovenia. So I think it will be good maybe that we discuss together.
Mm-hmm. Yeah.
Thank you.
Thank you.
Okay, thank you. I think that's it for questions for now. Of course, don't hesitate to put questions in the chat if some questions might arrive later on. And I think we can now leave the floor to Elke and Christian for their presentation.
All right. Can you hear me?
I hear you perfectly. Thank you.
Okay, perfect. Thanks so much for the interesting presentation about the cave, from the cave to the mine. Christian and I would like to tell you something about fluorescent tracer dyes in mining influenced water. We call it short MIW. So let's start. First of all, we need to talk about why we use tracer tests in mining influenced water. A few bullet points for you. We want to investigate if the mine water can pollute the surrounding groundwater. With tracer tests, the location and the reliability of dams can be proven. This is a picture of a former uranium mine in Germany where there was big leakage with the dam, so for dam investigation. Then for the flooding process after mine closure, a little bit later, I will talk about the hydrodynamics in flooded underground mines. So for the audience that is not familiar with mining, to explain what is going on inside a flooded underground mine. Then the flow of water within the flooded mine, which is a little bit comparable to the caves. Then drainage of contaminated mine water, and the duration of water treatment. On this picture here, you can see a settlement pond, and we wanted to figure out if the water is nicely, evenly flowing through the settlement pond so that there is enough time that the iron in this case can settle down. But it's not, because as you can see with the dye very nicely that the water is taking a shortcut. Then pollution control by mine geometry and mass transport, so to see if pollutants are carried out of the mine with the mine water. First of all, I would like to introduce which traces can be used in mines. So on the one side, there are natural traces like environmental isotopes or environmental chemicals or organisms like bacteria or physical effects. An example for a physical effect is this one. We measured at a river that is influenced by mine water, and we wanted to know where is the mine discharging into the river. So we measured the electrical conductivity over the length of this river. And at the first peak, you can see me there in the picture at the mine water discharge, we could clearly see an increase of the electrical conductivity. The two peaks that are going down are also mine water discharges, but then you have to take care. Not everything is mine water, because the third peak here that is going up, this was from a sewage treatment plant. Okay, on the other side, there are also artificial tracers, water-soluble tracers like uranine, and water-insoluble traces like spores. Latin name is Lycopodium clavatum. In this case, with the orange and yellowish color, it's colored, the spores, or microspheres, and these are like little tiny balls that are added into the water. So we talked about which traces can be used, but we need to discuss which traces have been used in mines so far. So to say before, it is very important before you conduct a tracer test, especially a tracer test in flooded underground mines, that the amount of tracer that will be added should be calculated. And we usually use the software Efficient Hydrologic Tracer Test Design, EHDT, to calculate the amount of tracer to be added. And this can be used for several types of tracer. So for example, in mine water, we used Lycopodium clavatum, the spores, and for the mine water tracer test, we used 1000 gram. Then microspheres, these little tiny balls, 20 to 40 milliliter. Then NaCl, sodium chloride, just normal table salt. If you use small amounts, we just go to the shops and buy a few bags, and big amounts, obviously we have to order it. And the amount that we used for mine water tracer test varies very, very much. So from 0.5 kilogram to 11,000 kilogram of table salt, which was in 30,000 liters of salt. I will show you a picture a little bit later. A massive mine water tracer test here in South Africa. Then potassium bromide, 3 kilogram, lithium bromide, 2 kilogram, uranine, you all know uranine, also called sodium fluorescent. And just to mention, in some countries, people just say fluorescent, which is not correct. You always need to call it sodium fluorescent. And until now, we used 2 kilogram, but we planned 2 very huge tracer tests, one in South Africa and one in Germany with 100 kilogram and 300 kilogram. Then eosine Y as a dye tracer, 1 kilogram, tinopal CBX, 3 kilogram, and rhodamine B, 400 gram. So these are the tracers that have been used in mines so far. Oh, and the physical effects, what I explained just before. But which are the fluorescent tracer dyes, because this is the title of our presentation. The fluorescent tracer dyes, you can see them here in this table with the CAS number, the detection limit, and the sorptivity, just to give you an overview. And the ones we are usually using are uranine, eosine Y, and tinopal CBSX. But other people use other tracers, but we recommend not to use them for mine water tracer tests because, or in general for tracer tests, because they are toxic. And now we're talking about sulforhodamine G, sulforhodamine B, rhodamine B, and rhodamine WT. So just keep this in mind. Now, I told you that I would like to explain hydrodynamics in flooded mines so that you understand what is going on in a flooded underground mine. This is a cross-section of a former iron ore mine in Germany, and you see a lot of shafts that are going down and horizontal are the levels that are partially connected with each other. So when the mining activity is done, the miners switch off the pumps, and then due to infiltration water and inflowing groundwater, the mine gets flooded. You can see this here with the blue frame. That is the water body. Now, there is also flow inside the mine because the mine water is flowing down to the lowest hydraulic level, which is in this case here, the valve edit where the water is flowing out of the mine. And obviously it doesn't have to be only one point of discharge. It can also be several points of discharges. This really depends on the setup of the mine. So there is a general flow direction inside the mine, but in mines, there can be also flow, and you see this down here, between shafts, a convection cell where water is flowing up and then it's flowing horizontally and then it's flowing down. There are convection cells, but the water can even flow within a shaft, up and down. So when you conduct tracer tests, this is something to keep in mind, that the water could also flow somewhere in some parts and own hydrodynamic processes there. Now we talked about the hydrodynamics, and back to the tracer test itself, the tracer injection. For mining influenced waters, it can be surface water discharged from a mine, and the injection can be done on a relatively small scale with a canister, but also with a hose. I mentioned the 30,000 liters. That was a tracer test with mining influenced water here in South Africa. So very different amount of tracers. But now probably new for you that the tracer test can also be done inside the mine, in the underground. So one example is, or one option is to add the tracer to the water surface here with a canister, or you just can also pour it in directly into the shaft without using a funnel. And then the other option is to lower down a device we have to a specific depth, let's say 300 meters depth or 500 meters depth. And then this device opens and releases the tracer at a certain depth we want to have it in the mine. Let's say at the second onsetting station, so where the gallery is connected to the shaft. And this is a very different and unique option to conduct the tracer test. Tracer sampling. After injection, we also need to sample the tracer. And it's important to keep in mind that there can be one sampling location, but also several sampling locations because there could be different discharge points from the shaft. It's better to have too much than too few of them. And you must be able to reach in time to your sampling locations. So set up everything before the tracer already arrives. Then it's also important to keep in mind that nearby sites could be hydraulically separated from each other. So although they are very close to each other, there could be no hydraulic connection. And of course, there are also worse things that can happen. And these are negative results due to incorrect selection of injection and sampling sites. And a mine is quite challenging. So, and sometimes there are no maps anymore available if the mine was already closed a long time ago. And it's a bit digging in the dark. So you have to be careful to choose the correct injection and sampling sites. Then also important to take field notes. For example, when you change your plan and you have to adjust because the injection site you planned is not accessible, and to be open to surprises. And here on this picture, I have an example for you for such a surprise. So we conducted a tracer test at a mine, and we started our sampling, and then coming back after 8 weeks, the fluorometer was completely black and completely clogged, and our data was, well, not really usable because we didn't have data because the fluorometer didn't really work due to the clogging. Duration of mine water tracer tests. First of all, it is important for a mine water tracer test to start with a conceptual model. And usually we draw this by hand. This is a Finnish mine with 2 shafts that is connected mainly on one level. And you can see that it's very important to understand how the water is flowing inside the mine and what we have to expect. Also, for example, to use the right amount of tracer. So to the duration of mine water tracer tests, it really depends on the mine layout. Mines can be very different. The shafts can be only 200 meters away from each other, but the shafts can also be 20 kilometers away from each other. So the duration of the mine water tests can be from 8 hours, 1 day. And the longest one we conducted was this Finnish mine, where the mine water tracer test took us 3.5 years. Now, effective velocities in flooded mines. To our knowledge, there are 55 tracer tests in mining influenced water between 1969 and this year. And the average effective velocity is between 0.011 and 1.82 meter per minute. And this is the 80% confidence interval. The slowest one, I don't read it out, you can read it by yourself. Very slow, water was basically standing. The fastest one, 11 meter per minute. So the water is really flowing through the mine. But the median is around 0.15 meter per minute and the mean value 0.85 meter per minute. Here you can see a table of a few tests. And it is always around 1 meter per minute. It doesn't matter which mine setup. It doesn't matter where the mine is. In most cases, the average effective velocity is around 1 meter per minute. And maybe this is a question to you. We don't know why this is the case. I mean, the mine setup is sometimes quite different, but it's always around 1 meter per minute. If you want to have a look at all the tracer tests that we conducted or that are in literature, you can check out Christian's webpage. Down there is the address, the link, and you can see all the tracer tests with the flow velocities and all the necessary information. And now I would like to hand over to Chris, because we would like to tell you more about different tracer tests and the big variety we found.
I really would have liked to speak about all the 37 mine water tracer tests that I conducted in the past 30 years, but then we would be here tomorrow morning. That's not a good idea. So Elke and I selected 3 of them. We selected these 3 because they show you 3 different setups, and they're from 3 different regions. So the first one I'm going to talk about is Metsämontu in Finland, which is an abandoned polymetallic mine, and we use uranine and Eocene Y. The next one is the tracer test that Elke already spoke about in the East Trend here in South Africa along the Lesbos-Route. And we wanted to find out something about a mining influence stream. And then finally, a tracer test that we conducted only a couple of months ago, 2 months ago in Bulembo. That's in Eswatini. You still might know it as Swaziland. And that's at the abandoned Havelok asbestos mine where we used sodium fluorescent. Let's come to Finland. That's a tracer test that lasted 3.5 years. So here you see the capital of Finland, Helsinki, the former capital of Turku, and Metsämontu is an abandoned mine site between Helsinki and Turku. And those of you who know the company Fiskars with the knives and the scissors, that's just around the corner so that you know roughly where it is. Now, sorry for second. Let's have a look to the mine layout first. So that's from a 1970 publication. You can clearly see that we have two shafts. One I called MSD. Here you can see a picture of it. It's 250 meters deep. And the other one, it's 330 meters away from this one. It's Metsamento shaft number 2. When it was constructed in 1980s, the deepest shaft in Finland with roughly 600 meters. Then there are 3 relevant working levels. Here it seems as if the 135 connects these 2 shafts. That's not the case. The reason why it looks like that is just because the 2 ore bodies are striking in different directions, but the connection is on the level 190. So 190 connects shaft 2 with shaft 1. The tracers that we used and the methods that we used is what Elke already mentioned. It's called the Lydia method. Lydia means lycopodium apparatus because I initially developed it for my PhD thesis 30 years ago, where I used lycopodium. So we are lowering it with a winch, in that case into a depth of 100 meters. And we conducted 2 tests, 0.5 kilogram and 700 grams of eosine Y. And here in shaft number 2, where we lowered the probes to a depth of 190 meters into the flooded mine water, we use 2 kilograms of uranium. Elke already said that we always calculate the amount of tracer we need to use with EHTD. We never use more than necessary to detect it with fluorimeters. We never use too much sodium fluorescein or any other tracer dye. We don't want people to see that we are dyeing streams. So that's the background for it. Therefore, the numbers are relatively low. Let me come to the breakthrough curve, and that looks a little bit different of what you might see. Here, that's the concentration on the left side for the eosine Y in micrograms per liter. And on the right side, that's for the sodium fluorescein in micrograms per liter. We always use micrograms. We never use the ppb and pp whatever, because UPAC and the SI are not allowing these units. So we are strictly following UPAC and SI rules. You can see the breakthrough curve for the sodium fluorescein, that is here. And you can see the breakthrough curve for the eosine Y. So the eosine Y was injected in shaft number 1 at a depth of 100 meters. And you can see the water is flowing upward from 100 meters to the discharge point with a clear peak here. The data has not been evaluated, so I cannot tell you some more details. I'm just showing the breakthrough curve. And you can see here that the sodium fluorescein, it always has peaks, then it goes down, as you know it from stream gorging. And the reason for that is always when there is a heavy rain event, then the tracer is flushed out from that 190 meters depth to the shaft number 1, and then in shaft number 1 to discharge into the local environment. So that's how it looks like. Let me give you a couple of numbers for the tracer test. Here's the mine again. Here are the 2 shafts. We injected the uranium at a depth of 190 meters in shaft 2, and the eosine Y at a depth of 100 meters in shaft number 1. These were the injection times. These were the peak times. We used the 2 different peaks that we saw there in the data. I know they were not very clear, but we wanted to know the first tracer arrival. Here are the distances, and here is the velocity. So you can clearly see in that case that no matter when the tracer arrives, it's roughly between 1.5 and 1.9 meters per day. That is correct. So the effective velocity is including the error ranges between 1.5 and 1.9 meters per day, which results in 1 millimeters per minute. And you can clearly see the water there, Elke said that before, is roughly standing in that mine. So that's one of the mines that we choose to understand and find out why in some mines the mine water is flowing extremely slowly. So that was the background for that tracer test here. It was not 1 meter per minute. Let's come to the next one. And we are just giving you in those three examples a little bit like a spotlight, not going into the details as we heard it in the previous presentation. That looks a little bit complicated. Here is the scale, here's the north arrow, and the color code that you see here, that's the depth of the gold reefs below surface. So that brownish color means that the gold reef comes to the surface, and that greenish color here means that the gold reefs are going down very deep. You can see that's roughly 2,000 meters here. The background for that study is we want to understand how much of the water of that stream, that red stream is the Blessbox-Buit, is discharging into the underground and is then treated in that mine water treatment plant that is here. So there's a shaft that goes, shaft number 3, that goes into the abandoned mine workings, pumps the water and treats it. The question is, where does the water come from? So I have a couple of lines here. These lines indicate where the Blessbox-Buit is crossing the outcrops of the gold reefs. That's also where illegal miners are working and are working into the underground. And we want to understand where exactly does the water flow into the underground and how long does it take until it reaches the mine water treatment plant. We also want to know if there is some recirculation of the water. You see here they are discharging here, then the water is flowing down. It could be that the water of the Blessbox-Buit is re-infiltrating into the underground and it's pumped back to the mine workings here. And therefore, we also needed to know the velocity of the water in the Blessbox. And that's the image that Elke showed you. We had 30,000 liters of saturated brine, which equals 11.4 kilograms of sodium chloride. We injected it into the stream. And then along the stream, we had a number of electrical conductivity meters. We had 8 in total. 4 were stolen. That's a problem here in South Africa. Vandalism for research equipment is very high. That's the reason why I only have 4 curves for you. What you can see is that you cannot see much. That's a problem that we had there in the stream. The fluctuation of the stream electrical conductivity was in the range of what we wanted to see. So that's the peak that we are interested in. You can clearly see before the peak arrives, the electrical conductivity goes down. The reason for that is ion exchange. So calcium and sodium are exchanged. Therefore, the electrical conductivity first goes down and then it goes up again. So that's the peak at the closest injection location. And then we heard it in the previous talk already. The longer the flow distance, the smaller gets the peak. So here you can see it again, here you can see it again, and the light one is somewhere here. So we used correlation analysis to find out where and how is the peak moving along the stream. So that's just a pre-test. This test will, when we start in about 4 to 6 weeks, use 100 kilograms of tracers, 33 kilograms of uranine, eosine Y, and tinopal CBX. Now the last example, that's Bulembo in Eswatini, and that is an abandoned asbestos mine at one stage, and that's a photograph from the 1980s. It was the 4th largest asbestos mine in the world. Here you can see the open pit where they started to mine the asbestos, and then they mined underground to a depth of roughly 1,000 meters. And here was the plant where they separated, cleaned, and packed the asbestos. Last year it looked like that. You can see that most of the plants are gone here. That one is the asbestos tailings. They backfilled mostly the open pit mine with reworked asbestos. And here is the main vertical shaft where we injected the tracer, which you will see in a moment. And at a distance along that valley of 1.1 kilometers away from the shaft, this is where the mine water discharges. It's roughly 2,000 liters per minute of mine water. We just injected the tracer through a borehole that we had in the main vertical shaft. You can see he's wearing a mask. That's not because of Corona. Always when we work on that site, we are wearing masks to ensure that we are not getting intoxicated with asbestos. And we had 500 grams of sodium fluorescent here. And we just put it into the shaft. The mine water level is 100 meters below us. And that was done without a pre-calculation of EHTD. I just guessed roughly how the mine might look like underground and how much we used based on our previous tracer tests. So we are using even the last little drop. Now, where did we sample? We sampled at the outflow, and we used the GGUN data logger for surface water here. So we always add a funnel so that the water flows nicely into the data, not into the data logger, but into the sampler. And then we have, you can see that white thing, we have a hose or a tube about 2 meters long so that there's an under pressure and the water flows nicely through that device. That cable goes to the data logger, which we nicely stored away so that people won't see it and we won't get vandalism. This is the breakthrough curve, and it's a very interesting breakthrough curve. The blue is the concentration for the sodium fluorescent. You see up to 8 micrograms per liter. Then there's a steep decline here, which we don't know yet where that comes from. But what we clearly can see that there must be two flow paths, flow path 1, flow path 2. The real reasons we don't know yet, as Elke indicated, you don't always have precise mine plans. The interesting thing is we got a recovery rate of 73%, and you can see that we are still not back at background concentrations. I already modeled that curve here to background concentration, and we had a recovery of roughly 85–90%. So that was that test in Bulembo, the latest one. As I said, it's just a little bit of an insight in what we are doing without going into all the details of these tests. So I thank you for your attention, and I want to finish. Oh, sorry, we have some data here. I apologize. So we had 138 meters per day or 10 centimeters per minute. And the data is usually using the median. The data is around the median of all the values that we measured so far in these 55 tests. And the last slide is again from Finland. Sometimes things can go very wrong. That's what you can see here. It's roughly 1 milliliter of saturated uranium, and that 1 milliliter is just from cleaning one of the glass bottles that are used to inject the tracer. So don't clean glass bottles in the field. And that's the end of Elke's and my presentation. Thanks very much for listening.
Thank you very much, Elke and Christian. Again, if there are questions, don't hesitate to raise your hands or ask them in a chat. If there are no, I do have a question actually. Is there, so there's different types of tracers that you can use in mine tracer tests, but how big is the impact of the water or like the chemical quality of the water on these tracers? Do you really have to take this into account, or doesn't it matter that much?
Yeah, it substantially matters. The very, very first tracer test that I did was in highly contaminated mine water in uranium mine. I could quickly find out also because the volume of that mine was extremely big. I could not use dyes because of the pH value and the contamination. I could not use any salts. We calculated it, we would have had to use between 20 and 50 tons of various salts, and then the density would have been so high that we would have found it somewhere. So I developed a method based on karst tracing, and I used stained lycopodium spores. We used 4 different colors of lycopodium spores. That was the first test. And the second mine water tracer test that I conducted with 6 injection points and 3 sampling points was with microspheres. For the same reason, I could not use any dye tracers and we could not use any salt tracers for that case. When the water quality is not too bad, we are using dye tracers. And meanwhile, we also developed a method to back calculate the concentration based on the pH value and the iron concentration in the water.
Is there somewhere where people that do mine tracer tests, can they find this information somewhere, or?
The last data that I mentioned is not published yet, but all the other information is published in my 2008 book and in the 2022 book in German and 2023 book in English. And I published already about, I think, 10 or 20 papers about mine water tracing where everything is described, so that you usually should be able to conduct a mine water tracer test. Not really, you should ask us.
Which I guess we can all find on your website, which is...
That's correct. Yeah.
Christian Wolkersdorfer,
as I said,
or just Wolkersdorfer?
Yeah, just Wolkersdorfer. Wolkersdorfer.info and then publications. As we already said, everything we are doing is freely available at any time.
I have another question. It's more like practically, how do you release tracer at, like, for example, 300 meter depth? Like, how do you know that the tracer is actually released at that depth?
That's one of the information we do not want to release because we want you to employ us.
Okay. Very clear.
But it's a Lydia method. The Lydia method has been described. But that answer I really don't want to give for now. A little bit of expert knowledge you have to keep all the time. You know that as well, Sophie.
Of course. Maybe it's also nice if you could tell us a bit about the Kassel 23 conference that is coming up.
Yeah, for those of you who are close to Germany, Elke and I started to organize German mine water conference last year in Kassel, because that's the center of Germany and everyone can come relatively closely to Kassel. We have exhibitors, and this year Trakwa and Sophie will be one of the exhibitors showing her device that they developed for analyzing tracers, dye tracers. We are expecting 100 colleagues to be in Kassel this year. We will see 20 presentations, and we currently have 10 exhibitors. They will all show their products and they will assist in answering questions. You still can register.
Perfect. So the information you can find in the chat, Elke just shared it, the link to the Christian's website, as well as the link to the Kassel conference website. If there are no more questions, I think, well, first of all, thank you very much, Elke and Christian, and I think we can go and listen to the last presentation for today.
Thank you. Merci bien, Sophie.
You're welcome. No, Pierre, we can see your presentation.
Okay, perfect. You hear me too? Yeah, okay. So thank you for having me. It's a nice opportunity to present our work, because we also use a tracer technique, but not in the classical approach of injecting a tracer at a point and monitoring the breakthrough at another point. We actually use the tracer to directly measure and monitor groundwater fluxes or Darcy fluxes in aquifer by measurement in existing monitoring wells. So our technique has applications for general hydrogeological characterization, of course, but also and specifically for contaminated aquifer management. So in the case I'm presenting today, I will talk about contaminated drinking water abstraction well. So we are here in Belgium in an aquifer that is made of sandstone and limestones. And such aquifers are usually good drinking water resources, except, of course, when they are contaminated with industrial pollutants. And here the drinking water abstraction well of interest is contaminated by chlorinated solvents. The thing is, the origin of the pollution, the source of the chlorinated solvent is not known. There are potentially two industries that could have been using the chlorinated solvent in their process, but which one is actually polluting, or is it another one? So prior to this study, we don't know. And the abstraction well is very important for the water producers. There are currently they are still using the water from that well because they can mix this water with water from other wells to decrease the chlorinated solvent concentration lower to the one that is prescribed in threshold value, and also because before the water goes through the drinking water network, the water has to go through a small treatment, and during this treatment, the majority of the chlorinated solvent is volatilized. So it's not really a huge problem, but it's still quite concerning because, yeah, it has to be solved. So our objective there was mainly to better constrain the conceptual model of the site. So, and with the ultimate goal is to bring elements to locate the source of chlorinated solvents. So to reach this goal, we suggested to apply a flux-based characterization approach. So on the field, we perform the classical groundwater sampling. We did the sampling in depth average on two monitoring wells around the pumping well and also at the pumping well, and we also perform groundwater flux measurement on the two monitoring wells to better quantify the flux around the well. So if we look at the result of the concentration of chlorinated solvent, we could see that we have the same concentration at the monitoring well located north of the pumping well, and it was about 18 microgram per liter. And the second monitoring well, MW27, that is located on southeast, concentration is lower at 10 microgram per liter, but there is still chlorinated solvents there. This was for a depth average sampling. When we sample in logging mode, let's say we perform like 3 meters intervals because we separate intervals with packers, with inflatable packers, to be able to sample at dedicated depth. And here we could see that the concentration are quite homogeneous vertically, so a bit of variation, but nothing really significant. So most of the time, when consulting company try to investigate a pollution problem, they are stuck in that concentration-based approach. And on that concentration-based approach, it was impossible to say whether the chlorinated solvents are coming from the north or from the southeast, or a bit of both. So we continue that study with a much more relevant flux-based approach, which includes, of course, our technology of groundwater flux measurement. And this technology is based on my PhD research that I did in the University of Liège in Belgium. So it consists in a single well tracer dilution experiment. So this experiment requires, of course, a tracer that is injected at a low and constant flow rate. So I don't know if some of you are familiar with the point dilution method. When you use a point dilution method, you inject the tracer at once in a well, and you monitor the decreasing of the tracer concentration in the well. And if the concentration in the well decreases fast, then it means that you have a high groundwater flow rate. Here, the difference is that we inject the tracer continuously. And of course, we also monitor the concentration of the tracer in the well. And for that, we can use the Aqua stream fluorimeter when we use fluorescent dye tracer. Or alternatively, we can use like salt tracer like potassium chloride and simply follow the electric conductivity of the water. So what we do basically is we measure the dilution of the tracer in our monitoring well. And this dilution is proportional to the groundwater flux that passes horizontally in the screen, through the screen of the well. So our result is representative of the whole thickness of the screen, but we can also limit this interval to target specific horizon or to apply a kind of logging mode to investigate the vertical heterogeneity of the fluxes along the vertical axis of the well. For example, we already used that technique in fractured aquifer a few years ago to quantify very precisely the groundwater fluxes in a specific fracture that has been identified previously by camera logging inspections. So it is something that we can do. So the first result was for the depth average. Oh no, sorry. Just a word about how it works in practice. So as I said, we inject continuously the tracer in the monitoring well. So at the beginning of the test, we don't have any tracer in our well. So we start the injection, and the concentration of the tracer rises, and then stabilized at a concentration that is actually a concentration that is reached when we have an equilibrium between the tracer that we inject in the well and the tracer that is flushed out of the well by the groundwater flux. And this stabilized concentration compared to the injected concentration of tracer allows the calculation of a dilution factor, which is proportional to the groundwater flux. And we really need to reach this stabilization because it allows us to deliver a very precise flux result. So basically, it takes 2 to 48 hours to get to the stabilized concentration. Of course, it's as a function of the groundwater flux. If the groundwater flux is very high, it's very fast, and we can have it sometimes in less than 1 hour. But most of the time, we implement the monitoring well one day. We let the experiment run until the next day, and then we have the data we need, and we can go to another well. So that's exactly what we did on the 2 monitoring wells. And firstly, it was just the depth average measurement, so to have the average flux on the wall thickness of the screen. And here are the results. We got nothing. So why? Just because the 2 monitoring wells are located 20 meters apart from the pumping well. And the pumping well is pumping at 150 cubic meter an hour, so quite an important flow rate. And in fact, the groundwater flux is so high around the pumping well that the tracer injected at the top of the water column in the monitoring well doesn't get to reach the bottom of the well and get flushed out of the well in the first meter of the screen. So the tracer doesn't reach the circulation pump that brings the water up to the surface and make it go through our equipment. So we did not recover any tracer and the test failed. But it's really not a problem, because if the flux is really high, then it means that the duration of the experiment will be quite short. So that's good for us, and that we can apply the technique in logging mode, and it won't take a lot of time to get the results. So this is an example of the result in one of the intervals that we tested on one well. So this is the experimental data. Of course, you have the concentration versus time. You see at the beginning of the experiment that the concentration rises, then stabilized, and then we stop the injection of tracer and the concentration decrease back to the background. So we interpret that that curve with an analytical solution that we can adjust manually the groundwater flux in the aquifer to fit the analytical solution to the observed value. And we also have a code that that automatically adjusts the groundwater flux and also estimate the uncertainties around the adjusted groundwater flux. So we did that on five intervals of each of the two wells, and we get groundwater fluxes ranging from 3 10 to minus 6 to 4 10 to minus 4 meter per second. So in fact, 2 orders of magnitude of variation in flux, really in the vicinity of the pumping well. And the highest flux was observed in the monitoring well 12, so the one located in the north of the pumping well, between 9 and 12 meters below the ground. And the lower fluxes were always observed in the deepest intervals, so around 18 to 12 meters below the ground surface. So here are the results, a bit more visually represented. So we could see the different fluxes in the different intervals of the wells. So these are just fluxes. So it's of course it's Darcy fluxing expressed in meter per second. But if you consider that that the flow surface has a width of 1 meter around the piezometer, where around the monitoring well where the fluxes are measured, we could say that in the monitoring well 27, the one in the southeast, there are actually 2.1 cubic meter per hour passing through this this well, and on the northern monitoring well, it was around 6 cubic meter an hour. So it means that the groundwater that comes to the pumping well is mainly coming from the north. So this was just for the Darcy flux, for the groundwater flux. But then we can go a bit further and look at the pollutant mass flux. And how do you get a pollutant mass flux? It's just a matter of multiplying the groundwater flux by the concentration of the chlorinated solvent here. And we got the flux of chlorinated solvent in milligram per day and per square meter. So we could see that since the concentration of chlorinated solvent were quite homogeneous vertically, the chlorinated solvent mass flux heterogeneity is governed by the groundwater flux. So it means that at the monitoring well 12, the one in the northern part, we have a really, really high chlorinated solvent flux that, of course, let's say, flow through this location, and mainly located between 9 and 12 meters below the surface. Again, this kind of flux result is representative just at the location of the well, and it's milligram per day and per square meter. But if we consider a surface, let's say a flow surface that is representative of that measurement around the well, and we consider the surface of being 1 meter in width, then we can calculate the mass discharge. So the mass discharge of chlorinated solvent, which is really a mass per unit of time that is flowing through that section. And for the monitoring well in the southeast, so the 27, we got 0.5 gram per day. So it means that 0.5 gram per day of chlorinated solvent is actually flowing or transiting by that location and will reach the pumping well. At the north monitoring well, the MW12, we got a mass discharge of chlorinated solvent of 2.6 milligram per day. No, the units are not correct. The first one is 0.5 milligram per day and 2.6 gram per day. And also again mainly on of course in the upper intervals in the monitoring well 12. So it means that if you look at the mass discharge around the pumping well, we have a chlorinated solvent mass discharge that is 5 times higher in the north than the one that is measured in the southeast. So that mainly orients us toward the source of the chlorinated solvent that is located north of the pumping well. And of course, that it means that 83% of the chlorinated solvent discharge comes from this monitoring well located in the north. And in the meantime, other investigation performed by the Public Drinking Water Company also oriented the investigation in the industrial sites located in the north. And that is very unlikely that that the chlorinated solvent is also coming from the east. But then, how come that we can find chlorinated solvent in the piezometer 27 if the pollutant is coming from the north? And it means that maybe the water is coming from the north, spread a bit, and then is catch anyway in the radial conversion flow around the well. But for that, the whole mass discharge that is pumped out of the obstruction well should come realistically from the north. And actually, we can calculate that. So we know the obstruction flow rate of the pumping well, which is 148 cubic meter an hour, and we know the concentration of the chlorinated solvent that we get out of the pumping well. So we know that we have a chlorinated solvent mass discharge at the pumping well that is 64 grams per day. So knowing this mass discharge recovered at the pumping well and knowing the mass flux that we measure at the monitoring well 12, what is the width of the flow surface that is necessary to induce this 64 grams per day? And it's a matter of simple a division. It's a simple arithmetic division, and we can find that if the chlorinated solvent mass flux that we measure at MW12 is representative of a surface that has a width of 24 meters, it's enough to feed all the chlorinated solvent that we find in the pumping well. So then you can actually transform that 24 meter and project, let's say, this width on the circle around the well, and you can find a kind of angle from which the chlorinated solvent can come from. And in fact, it was later shown that actually the chlorinated solvent source were in fact located in the north industrial site that we could see here with some cars and some lorries, and actually it was the correct let's say the correct location for the chlorinated solvent. So what we were able to tell is that most of the chlorinated solvent comes from the well located in the north, and that a source of chlorinated solvent coming from the area located there in the yellow part could justify the amount of chlorinated solvent that is coming in the pumping well. So as I said, so complementary studies had to be done, of course, to prove the location of the source, and in fact that is still studies that are ongoing, but there are new monitoring wells that are drilled close to this industry to find exactly where is the source. So that was was an example that what could be done with the flux technique. There are a lot of other application, of course, but one of the main, let's say, outcome of this study is that when you deal with a contaminated site, it's most of the time it's interesting to go a bit further than the classical concentration-based approach, and not only look at what is the concentration that I have in the aquifer, but to go to a flux-based approach and to try to look at what is the mass of pollutant that is actually flowing, that is actually moving. It's much more relevant when you're dealing with a dispersion risk of pollutant in aquifer. So that was it. Thank you for your attention.
Thank you very much, Pierre. If there are questions, don't hesitate to ask. Christian has a question for you. Go ahead, Christian.
Merci bien, Pierre. Me again.
Yeah.
A city near Karlsruhe, a village near Karlsruhe in Germany, about it was in 1990, had a very similar problem. They constructed a motorway, and on the left side of the motorway was a US Army supermarket, shopping market, which was heated with a heater, and they used diesel fuel.
Yeah.
On the right side of the motorway that they newly constructed there was a car company. So the car company claimed the petrol that they found, the petrol contamination or the hydrocarbon contamination that they found while they constructed the motorway is from the US Army, and the US Army claimed, no, it cannot be from us. It must be from that car company. So I'm coming to my question. What they did was they analyzed the isotopic structure of the isotopic composition of the hydrocarbon. So Pierre, you said that you still want to do some more investigations. Is that something you are taking into consideration as well? Trying to find out what is the potential source on the north, what is the potential source on the south, getting samples from there, and then trying to find out, this is the isotopic composition, it's coming from there.
Yes, in fact, it's something that we can do. I don't think it will be applied there because actually the company in the south used actually other types of chlorinated solvent, and the one that is found in the north is really the same. It's really a TCE trichloroethene, so it's really, I mean, it's a bit incriminating for them. But yeah, but in some cases, yes, isotopic composition we use that on different element, on carbon, on chloride, on but it's a good thing. For example, as I mentioned, when you have multiple sources, if you apply mass discharge and approach, you can really try to differentiate what sources are contributing to what extent to let's say a plume that is mixing with another plume, and also to differentiate the different origin. You can analyze isotopes. So sometimes but I mean it's not a classical approach that we use on a daily basis. It's really exceptional when you do it.
Not to misinterpret me, your results are really good. I liked it very much.
It
just would help because you're a company now. You need to prove, or I think you need to prove that whatever you did is correct, because it's a relatively new method and people will question that method. And if you come up with an additional result, then you could easily prove, look, my method is okay. It can be supported by the isotopic data, and that would make sure that you get more jobs, I think.
Yeah, of course. Yeah. That's why we are communicating a lot, and of course, I mean, it's based on the basic technique is based on my PhD thesis that has been, of course, published and that's available for everyone.
Yeah. Merci bien. Yeah, c'était très bien.
Thank you, Christian. Pierre, I also have a question. For the well, you used fluorescent dyes, or you
that's it. Yeah.
What wasn't there an issue with colored drinking water since it was flowing so quickly to the drinking well, or did I understand that?
No. It was a concern of the drinking water company, but since, as I said, we are not injecting tracer and recovering it and another well. We are actually measuring the tracer exactly at the point where we inject. So it means that we need a really small amount of tracer because we don't have a lot of dilution in our well. So for example, I think for 20-hour measurement, I use like 20 milligrams of fluorescent. So and then you dilute this 20 milligrams in that amount of groundwater that is pumped by the well, and I mean it was really nothing, and it was quite reassuring also for the water producer because they are always a bit afraid of coloring the water. Yeah. And on that side, it was the drinking water producer that insisted on us using fluorescent more than potassium chloride, for example.
Okay.
So,
well, thank you. If there are other questions, don't hesitate to ask them either in the chat by raising your hand, so maybe they can contact you afterwards.
Yes, of course. Of course. Then I can also in the chat just put a reminder of our website. Anyone has a question?
Okay, well, thank you very much, Romain, Christian, Elke, and Pierre for your presentations. I really liked that it's all very different. Like it's all using dye tracing or tracer tests, but for very different applications. So thank you very much. I hope the other participants enjoyed it, and we have a second series tomorrow at the same time. I hope to see you again there tomorrow as well. So this webinar has been recorded and will be made available, of course, with the permission of the presenters later on, after the second series is finished as well. And I wish you all a very good afternoon. Thank you.
Thanks, Sophie. Merci bien, Sophie. And good afternoon, everyone. And looking forward to seeing